Alright, it says that the integration from 0 to 3 x upon root of x plus 1 dx. Okay. Now, doing any type of integration question, you have to keep in mind there are only two parts of doing this. The first one is using u substitution, and the second is using parts integration in the parts method. And using these two methods, you can only do integration. You cannot use integration by, you cannot use the quotient rule or the product rule, as those two are only strictly for differentiation. I'll give a minute to try on this question. But for this question, we could use integration by parts, but it's always easy to try to use u substitution for a particular question, just because it's always easier. It's majority of the time it's u substitution. If u substitution doesn't work out, then definitely have to use either integration by parts or trigonometric substitution, or some other method which I will explain later on throughout the weeks. But in this simple case, so firstly, whenever you see integration question, always use u substitution. So if you could make a u substitute, I think definitely we could make a u substitution for x plus 1, this part. Okay, if we make x plus 1 is equal to u, okay, if we do that, meaning make our u is equal to x plus 1, alright. So in this case, in this particular case, you can actually, so once we have u is equal to x plus 1, we'll differentiate this so that we can put it back into our formula. Okay, so we just differentiate this with respect to dx, or whatever variable. If this was y, then du upon dy. Okay, so this is, sorry, this should have been du upon dx. Okay, du upon dx, which will, when we differentiate, will give us 1. Okay, so once we got that, okay, now we'll see. So once we've got that, and just to keep in mind, I will explain later on, we could also write this in terms of x. Okay, so if this is plus 1, we take it to the other side, this becomes u minus 1, which is equal to x. U minus 1 is equal to x. Okay, and in this, and then from this, using this formula, this, okay, using this we can actually write our limits. We'll have to first go on to do our limits part. Okay, so once we have determined that u is equal to x plus 1, we'll now do x is equal to u minus 1 as well. So once we differentiate this part, you can see that this part over here, this part, okay, du upon dx, like I said, is equal to 1. Du upon dx is equal to 1. Now, du upon dx is equal to 1 also. So in this case, obviously we can take the dx the other side. This becomes du is equal to dx. So du is equal to dx. So in this particular case, we now know that du is equal to dx. So if we substitute x is equal to 0 into this equation, in this particular equation, because once we substitute u into our equation, we will have to do everything in terms of u. Because in this, you can see this is our integral sign with respect to dx. With respect to dx, and this is dx, meaning our the lower limit, and this is our upper limit, and this is our lower limit. The upper and our lower limit is for x. You cannot have this as dy, and this your limits of integration would be in terms of x. In this, the with respect to whatever variable it is has to be in correlation with the upper limit and your lower limit. So in this case, so once we got to know that part, now we'll try to see if x is equal to 0, because that is our limits of integration. X is equal to 0, then u is equal to 0 plus 1, because we have already chosen our u, which is u is equal to x plus 1. Now if x is equal to 0, we're substituting over here y is equal to x. So 0 plus 1, so we got this, basically we got this from our general formula, which was here. So you can do this for any type of problem. Whatever you have identified, u is equal to x plus 1, or the question would have been x upon root of x plus 2, then you could have chosen u is equal to x plus 2. So whatever the equation that you have chosen to be u, that x or y value will be substituted into u, because we're using method 2 over here. Okay. So once you, because this is method 2 is basically an easy approach, so you don't have to convert it back into x, now x points, and then simplify. So in this case we'll just have u, so it's 0 plus 1, because x is equal to 0. Just substitute in this formula over here. This is 0 plus 1, which will give us 1, and then we have u is equal to 3 plus 1, and then 3 plus 1 would be basically 4. Okay, so in this part over here, so once we got our limits of integration from 1 to 4, okay, our limits of integration is 1 to 4. Now we get that part. Okay. Okay, so Shabnil, do you have any questions regarding anything that I've done so far? Okay, Shabnil, looks like there's still some technical difficulties. Never mind. I will still continue with this sample example. If you have any questions, do tap into the chat box. Okay. So we'll continue from where we left off. Okay. So our limit summation we got from 1 to 4, because this is in terms of du. Whatever we have in terms of, right, if this is du, then our limits of integration has to be in terms of du. Over here it was dx, and we got 0 to 3. The only reason how we got 1 to 4 was basically u was equal to x plus 1, and this is basically your u. So from this side-by-side comparison, you can see this is root of x plus 1, and we got root of u. Now you can see if we try to integrate this part directly, you can see with respect to u. We cannot integrate it directly just because there is an x. Unless otherwise it was stated that x was a constant, which we then could have taken it out of the integration. But since it's not stated, we have to take it into account that it's an equation. So in this case, you have to realize this, just like I've been told you before. So whenever you do a integration question, if you come to across like this type of situation where you have two variables, but with respect to something, the first variable and not the second, you can actually try and think that you could write the u substitution, whatever you have, to rearrange it so that you can fit it inside the integration and then carry it on. So in this case, in our case, was u minus 1 is equal to x. I took this plus 1 to the other side, which had become minus 1. Okay. So in this case, alright. So okay, there we go. U is equal to x is equal to u minus 1. So thus in this case, so our general formula, we have written this exact same question in terms of this. Okay, in terms of this. Now you can see that we have actually, in this part over here, we can check this is that this was x upon root u, and then we got stuck over here just because there was an x, in which we knew it was an constant, it was an equation. So, but we also knew that this was x, u minus 1 is equal to x. So we substitute that over here, u minus 1, which is equal to x. Now you can see in this part over here, everything is basically given, meaning everything is in terms of u. So we can actually do the integration part right now, just because everything is in terms of u. Okay, so in this example here we got from 1 to 4, and this is u minus 1 upon u. Okay, so in this case, now you can, since there is a common denominator meaning the lower number is equal for both, we can actually split them up. Alright? Okay, so this mistake, or this should have been root u. Sorry about that. So x is u minus 1, and then this is root 2, root u should have been carried over here. Okay, so in this case we can split them up, meaning we can split them up this way. So u upon root u would be over here, okay, in this part, and then minus, you have to take that minus, so it was, if it were positive, would have taken positive, and then this would have been 1 upon root u, 1 upon root. You can see this is root u and root u are common. Also you can, so basically if you had, let's say 1 upon 2 minus 1 upon 2, okay, that would have been 0, but in any other case, if the denominator is same, you can directly add or subtract it. Okay, so in this case, so again you have to, okay, one thing to keep in mind is always to keep on writing the limit, the integral sign, 1 to 4. Okay, you only remove the integral sign once you're making a substitution at this step over here. Okay, but at this case it's 1 to 4, so we'll integrate from 1 to 4 with respect to dx, du rather, and you also have to keep on writing du. Okay, you always have to keep on writing du until you make the substitution. So there should have been a du over here. Okay, so now in this case, okay, you can see that this is u upon root u minus 1 upon root u, and this you can see over here remains the same, but this part over here becomes root u. You have to wonder, this is u upon root u, how do you get to root u? I'll tell you how. Okay, do you have any guesses? Okay, so it was basically we had u upon root u. Okay, this is u. So u upon root u, how we got to this is basically, okay, so let's say I have an it's not a theorem actually, it's basically u times u can also be written as u root of u multiplied by, this is multiplied, okay, and then we have another root u, okay, divided by root u. Okay, this u can be written as root u times root u. Now, okay, so this is not like a theorem, but basically a simple trick to, it's like having a common denominator, okay, a common numerator. So in this case, you can see that it's u, so root u times root u. So okay, let's do this for example. We'll explain this. Okay, let's say if we have root u times root u, then what's root u times root u? Root square. This becomes u, and everything is squared. Okay, had this been just x times x, then it would have been x squared. So whatever this is root u, or whatever equation that you had would have been squared because it's multiplied. So root u times root u, it's root u everything squared. But we do know that the square root sign and root sign are, the squared and the square root sign are basically opposite. So this and this will cancel out, meaning you'll just have u left. Okay, just u left. So meaning we have now know that u can be written as root u times root u. Okay. So similarly in this case, this is why we have root u times root u, and then that root and that root will cancel, meaning you'll only have this root and this root will cancel, so you're only left with root u. Okay. Is this okay, Shabnil? Okay, I'll carry on then. So so from here, so it's root u minus 1 upon root u. Okay, thanks for the response, Shabnil. Okay, now so from here we'll see this is 1 upon u. So we have done nothing with the integration part, we have only simplified it, meaning making our work a lot easier. So this is, to be honest, this seemed a bit complicated, and this still needs to be done some work to it, but it's okay. So from here we can actually go to here. So this is root u minus 1 upon root u, okay, and then root u can be actually written as to the power half. Okay, root of anything, let's use x over here in this case, okay, will be basically x to the power half. Okay, x to the power half. In this case it's root u, so simply meaning u to the power half. And you bring the minus sign down, and this is 1 upon root u. So this is 1 upon root u, it's 1, okay, let's say we have 1 upon root u, okay. So now we know that 1 upon root u is basically 1 upon u to the power half, because we know you can either write root u or u to the power half, it means the same thing, it's equivalent. Okay, so now you can see whenever, okay, so this part is another, this is actually a rule, a principle in mathematics. If you have a variable raised to a power, if the power comes on top to the numerator, it actually becomes negative. Okay, so this becomes u to the power 1 upon half. So this could be for any case. Okay, let's take an example for 1 upon x cube. Okay, 1 upon x cube. So this, this is already in cube, x 1 upon x cube. So if you take it to the numerator, this would basically be x to the power minus 3. Okay, so similarly for anything 1 upon x to the power, 1 upon u to the power, 1 upon anything to the power, if you bring it on top to the numerator, so this is basically a simple form, it's just one variable, it's not 1 upon something, so x to the power 1 upon 3. Similarly, if you have any other questions when you're doing integration or basically integration, yeah, or sometimes differentiation, you have to know that these two can be rewritten as each other, and this will be very helpful at times. Okay, so that is why we have minus u to the power minus half, because root 2 becomes to the power half, and then on top to the numerator becomes negative half. And so basically from here what we did was we tried to integrate. Okay, since there's nothing more to simplify, this is simple integration. This has to keep on writing du. Okay, integration sign and du always has to come together unless you're making a substitution. Okay, so from here u to the power half, is basically what do you call, when you integrate, so the power 1 is added to the power and divided by whatever value we have left is divided by that whole equation. Okay, so in this case u to the power u to the power half plus 1, which is u to the power 3 upon 2, divided by 3 upon 2. Okay. Okay, so over here u to the power half. Okay, I'll do this separately. Okay, du, this is the integral sign. I integrate u to the power half du. Okay, so u to the power half in this case, u to the power half. Okay, so we can actually, so integration, whatever this whatever variable you have, you add 1 to the power, then divide by the result. Okay, so in this case would have been u half plus 1 divided by half plus 1. Okay, so this is basically the general integration rule. So u to the power half plus 1 would have been u to the power half plus 1, that's 3 upon 2. Okay, and then divide by 3 upon 2. Okay, but 3 upon, this is 1 upon 3 upon 2. So this part over here, the denominator, can be written as 2 upon 3 u to the power 3 upon 2. So this can be written like this. So meaning from here we got this. Okay, so it's u plus 1 upon the result, okay, which is half plus 1, so divide by half plus 1. So u to the power 3 upon 2 to divide by 3 upon 2 is equal to this, and so 3 upon 2 is divided by this, so it can be written as 2 upon 3 because it's 1 upon 3 upon 2, so you can rearrange that to 2 upon 3. Okay, you can also say that when the denominator comes on top, it switches. Okay, so this is basically it. So this could be the same as if you had 1 upon, let's say 2/3. Okay, 1 upon 2/5. Okay, if you have 1 upon 2/5, so this is basically 5 upon 2. Okay, so this is basically switch. Okay, so in this case over here, this is what happens. So it is half plus 1, we have been 3 upon 2 divided by 3 upon 2, but like I said before, you can change it because it would have been 1 divided by 3 upon 2, so basically 2 upon 3. Minus, you can see, so this half is a negative, so once we're integrating, we're adding 1 to the power. So negative half plus 1. So negative half plus 1, that's a half, and half you have to divide by 2. So this again would have been, in this case, 1 upon 1 upon 2. In this case, 1 upon 1 upon 2, because it's u to the power minus half, alright, and then you add 1 to that, it becomes u to the power half, and that's our result, divided by the result, which is 1 upon 1 to the power, because u to the power half would be over here. Okay, and so this could be 1 upon 1 upon 2 could be written as 2, and that is why this 2 is on top of here. Okay, so in the again you have to have a square bracket 1 to 4 because you haven't made a substitution yet. Now we just make a substitution. Okay, so 2 upon 3, the upper limit always goes first, so that's 4 to the power 3 upon 2 minus 2 into 4 to the power half, minus, because it's always the upper limit minus the lower limit and whatever function you have. So the 4 into the function minus 1 into the function. So we have substituted 4 into our function, which is here, minus we substitute 1 into our function. Okay, so in this case 4 to the power 3 upon 2 multiplied by 2 divided by 3 minus 2 into 4 to the power half, we will get 4 upon 3, and this will get a negative, and negative will become a positive. Okay, so we'll have 4 upon 3 plus 4 upon 3, which will be 8 upon 3. So this is our final answer, 8 upon 3. So that was this approach was a simple approach because we used use substitution. We could have also used the integration by parts method. That would have taken a lot of time. So it is always easier to always use substitution first. If you can use substitution, then you go on with it. If you can't, then definitely have to opt for something else. In this case, it was okay. We managed to do the problem, but if you cannot use substitution, then you have to opt for integration by parts. So trigonometric substitution. But definitely you cannot use product rule and quotient rule, because those two are only and only for differentiation. I've seen students who made this sort of mistake. Just this could be like a gentle reminder not to use product and quotient rule in integration, because product and quotient rule are only and only for differentiation. Okay, methods of integration include use substitution, trigonometric substitution, integration by parts, all those things. Okay, so is there any question, Shabnir? I hope I'm pronouncing your name correct, Shabnir.